Hello everyone. All right. Today we're going to be making our schematic for the hydroponic planter that we are building or have built. So today yeah, we're going to be using Easy EDA, woo, as you can see, and we are going to be creating our schematic for our controller. So the controller is going to have three things. So let's list this out right now. One, okay, let me straighten out the hands a bit. All right, one, we're going to have a controller involved. I'm thinking it might be the Wemos D1, just because it's a little bit easier to work with than ESP32. But I'm also thinking, okay, so it's got to have a controller. It's going to be either the D1 Mini or an ESP32. Two, we are going to have the ability, we need to have the ability to have control over the pump. That is the main reason we are doing this right now, because I need to have a controller that has the ability to control the pump. That's the main thing right now, because without that I can't plant anything, because otherwise they would dry up or the pump would be running 24/7, which is not an ideal solution. So we have to figure that out. We need to figure out how to turn the pump on and off. Okay, number three. It has to be controlled by some form of software. Right now, I'm thinking that it needs to, I'm going to use my home automation, my home assistant, in order to control it. We're going to be using home assistant to control it. So that is going to be what we're going to use just as a software. So that's easy. I don't know if I want LEDs or anything for it, to see what's on and what's off, because at nighttime, this is going to be in my room, and I really don't want those. I might just put one on there just for if I want to. Now, the optional things are, I kind of want light control just in case I put, like, you know, a set of lights in. So I want to do something with that. So we're going to do another, like, 12-volt control rail somewhere. And then what's the last thing we need to do? That's pretty much it. I might throw a sensor in. I might throw two switches on two places for switches, because it'll tell me there's sensors that can show you if there's a little bobber in them, so it'll display when it'll float high when the water's up, and then sink when it's not. And so I need a full and a low water kind of like sensor. Actually, that's what the light can be attached to. So like, if the water's low, then the light will come on. Actually, that's pretty good. Okay, so we got one light, 2 sensors, and 2 12-volt rails that we're going to need to control. And I think the D1 Mini can handle it. Alright, so we're going to do this as hydroponic controller V1 hydroponic tower controller V1. Alright. We're using easy EDA for this thing. Hydroponic tower controller. Alright. I'm just gonna import a bunch of things from another design I'm doing. Okay. So this is gonna be our controller, the D1 Mini. We're gonna have to have power. And we've got a 12 volt. Basically, we have 12 volt right there. All right. All right. So first things first. Let me. Alright, so first things first, we're going to ignore everything I just put on here. Besides the power. Alright, so power is going to be 12 volt power. Alright. So it's going to come in. This is for one of those, like, I forget what you call those connectors. The terminals. The screw-in terminals. So this is for a screw-in terminal right here. And what we're going to do is we're going to look up in the library. Okay, so we need to go from 12 volts. And this only does 5 volts. So we need to... Oh, it's already looked up. So we need a... I think a mini 650. Yeah, so this steps it down automatically to 5 volts. Yeah, output voltage 5 volts. All right, so this is something new. I've not worked with these before, but these are just supposed to be buck converters. So yeah, so buck converters are a lot better than not better, but they're more energy efficient than the regular 7805 regulators, because this one doesn't produce as much heat. These are more efficient. We're gonna use these guys, and hopefully that's a correct. All right. Wait. Oh, it does have one. Okay, so all right, because I have to make sure when you're doing this, when you're using user contributed ones, you have to make sure that it has the the board drawing, because otherwise, if it's just this one, it's just for the schematic. And you can't order the board without this. The board drawing, because that shows where all the pins are for this one. So we are going to flip this over. All right, so this is going to be out, so 5 volts out, positive. It's going to be there. Let's tidy that up. And then, all right, let's do ground, which is the minus. And then this one is just going to be whatever, because I like to do positives for number 1 and negatives for number 2. All right, so now the controller has power. All right. Now I need to go. Whoop. Wait, why am I still big? I should have been small. I'm so sorry. All right. So just in case anyone missed it, big streamer dumb move. I got so caught up in trying to explain everything that I forgot to make myself smaller. Anywho, so if y'all didn't see it before, if you see it through my big head, we got a terminal that's going to be for 12 volts. It's going to go into a DC to DC converter and step it down to 5 volts. That way the controller right over here can use it. Next, I need to actually, what were we gonna do? I don't know what we were gonna do. Oh, I was gonna check the pins for D1 mini pins, because there's certain pins you shouldn't use. Oh. Okay, so I can't use 3. I can't use 4. Yep, so I can't use, okay, so I can't use GPIO 0, GPIO 2, it needs to be high. I don't want any of these, I don't want to deal with it, so we're not going to deal with them. So 5, 4, 14, 2, 3, wait, what? 5, 4, 0 and 2. So I can't use 0 and 2. I want to keep 1 and 3 clear because that's the TX and RX, which yeah, needs to be high at boot, and we don't want to do that because we're also going to be using them to, I think that uses the Wi-Fi. I think that uses the Wi-Fi. So like when I'm trying to communicate it with Home Assistant, I don't think it'll like that. So we got 4 and 5 here, and that's it. What are we talking about? 16 high at boot, so no 16. 14, 12, 13. 14, 12, 13 are good. What about 15? Pulled to ground. Boot fails if pulled high. Wait, 1, 2, 3, 4, 5. And how many things do we need? We need two 12 volts. We need... What was I going for? Two 12 volts. Two sensors? I don't know. Dang it, I should have made a list. Okay, so we're gonna put these out. 12 volt lights. 12 volt pump. That's honestly what all I need is just the pump. Oh, and the LED. Wait, that's 5. I think that'll work. 5. Low. Low water. High water. So when the water's high, it's going to have the sensor for detecting if it's high. We're going to have a sensor for detecting if it's low. That way it doesn't kill the pump. We can stop the pump, and then we can also alert ourselves. I can probably make something in Home Assistant to alert me to ring my phone when it's low. Actually pretty good. And that's why I like to integrate Home Assistant with it, because like all these things can come together under one roof. I originally wanted to like make my own Home Assistant, then I'm like, too much coding. Alright. So 1, 2, 3, 4, and 5. We have 1, 2, 3, 4, 5. And then we also have an analog input. So in theory, we can throw another sensor on there. And if we use it, we use it. If not, then it just sits there. All right, so all right. All right, so let's get our full volt controllers in gear before we do the sensors, because sensors are easy. Mildly easy. I'm not gonna put it as 100% there, but it's good. Okay, so we have a lot of RF right, so IR FZ44 NP and 44 N. All right, so we have a lot of these. If you haven't been to this channel before, we use the IR FZ44 chips a lot, transistors. So basically how transistors work is, actually we're gonna do this as we do this. Cool. All Alright, so we have the drain, the source, and the gate. So normally how this would work is you'd have your control pin. Let's say, we say 4. It would go to the gate, and that controls whether the transistor is on or off. Then we would have 12 volts. 12 volts going into the pump, and then the ground here, and then this goes straight to ground. So when the gate's pressed, it turns on and creates that full circuit and goes around. But because I don't know if I really want it to go straight to the pins. Which one is okay? D1, D5. So D1, D2. Yeah, D1, D2. Okay. So instead of it going all the way through, because I forget if it's 5 volts from the pins or if it's 3.3 volts. Even still, I think I should have a voltage divider, because like 2.5 is the correct amount for... So in order for the gate to work properly, it needs to have a certain voltage, and I believe the voltage is 2.5. Which none of these stupid... Usually there's like a data sheet. Okay, so... Yeah, show me the data sheet. Come on. Okay, the gate threshold is 2, and the max is 4. So, anywhere from 2 to 4 volts will be needed to have this gate close and the circuit to be completed. So... kind of want... I know 3.3 volts falls in there. I'd be lazy and just do that. No, I still need to put in a... In theory, it should be fine, but there's also going to be amperage going through here, and... screw it. I'm just going to put a voltage divider in. I don't care. We'll figure out the values later. In theory, I shouldn't need it, but just in case I do, because sometimes these chips suck. And we're just gonna copy this. No! Ah! We're just gonna copy this design and just use it for the pump as well. Oop, nope. Okay, so it's gonna go there, there. So what a voltage divider does, it divides the voltage between two resistors. So it will, if you divide the voltage, half the voltage is on this one, and then the rest of the voltage gets passed through and used on this one. But that voltage that's in between also splits off and goes in the other direction towards the gate in this case. So hopefully that'll work. Alright, so we got our lights and the pump gone. Now we need our low water, our high water, and our analog sensors. So we're going to be using a 10K resistor for each of these. So what this does is we're going to use a 3.3 volt side, and it's going to connect to each one of these. And then it's going to go to ground, or to the resistor. Each one of these, yep, it goes to the resistor. These back a ways. And then they're all going to be connected to ground. Okay, now what we're going to be doing here is most things are basically either on or off, but for the controller to identify that, it needs to be either a fully on or fully off. Sometimes within the controller it messes itself up, and if something's giving it 0 volts, normally off, but we're just going to consider 0 volts off for this example. If it's off and giving 0 volts or giving no voltage at all, sometimes the controller will mess it up and it won't read it properly. So it'll kind of like skip around the voltage wise, unless it's grounded properly. So that's why right now, that's why we put these resistors on here. So A0, and we're gonna put it right in between the resistor and the signal. So if there is a signal, the 5 volts will come through here, go up, and go to the A0. It'll also go to the other, it'll go through the resistor, but because there's a resistor here, it'll want to travel through this wire up to the chip first. Now, if there's no voltage going through here, because the switch for the analog sensor turns itself off, and so there's 3.3 volts going in, but there's nothing coming out, well, then the 10K resistor will force the chip to go to ground. there's no connection in the analog sensor. So just pull it to ground. So this will be 0. That's the same way with each one of these other ones that we're gonna do. And if I could remember, okay, keeping out. Woo. All right, so 14, 5. And then 12. So we're wiring this up now. So that way 5 and 6 are okay. On this side over here on the left side, you can see that those are going to be okay to work. And so we just hook them up to the other sensors. Then we have 5, 6, and 7. So 7's going to be the LED. So we're going to be using a 5mm LED. In this example, it's red. What we're gonna do is, it's been a while since LED images diagram. I think plus is on this side and minus is on that side. Yep, okay, so alright, so we're gonna have it so so whenever I throw when the controller throws 3.3 volts, it's gonna light up the LED, go through the resistor, and then back to ground. And so that'll complete that circuit. But if the controller is not throwing any voltage, it'll just go as ground. And that's good. So I think this is what's gonna be okay for right now. I mean, I don't really trust it. E4. Yeah, because I think I trusted this at some point and it screwed me over. Oh, did we want to? No. We got lights. We got 12-volt light source. We got 12-volt pump. We got low high water and just a random analog signal just in case. We got an analog sensor just in case. I think that's good enough. We also got the converter. So you know what? Let's do it. So this is our schematic. Next, we're gonna put it onto a board and we're gonna see design PCB. Here we go. Nope, keep going. Alright, oh, nope. Alright, so this is just going to be, I guess, quick place. No, we are going to place it in a way where it actually will work. Because I've done that before where I've just done quick stuff and it's just not as good. What are we? 1 and 2, 3 and 4. Okay. And then I assume 2 here. Yep, 2's gonna be there. 3's gonna be there. 3 and 4. Oh. Mm-hmm. I don't know. Do I want heat sinks on them? Probably at some point. I should just design it for heat sinks in mind. What I'm doing is, so it imported all the designs onto this board, and right now we are just trying to get everything onto the PCB. The PCB is represented by the purple square. And we're trying to get these in kind of relatively close proximity, because the bigger the board, the more expensive it is. I really don't want it to be too expensive. Because again, this is just a prototype, to be honest. It really is just a prototype because I'm probably only going to make one of these. I'm probably not going to do anything outside of this. Okay. Okay, so what I want to do is I want to throw this there. We're going to turn that, and turn that. Oh. Oh. We're going to pull these up. LED up here. Turn it around. And we're going to try and get, like, you see where the lines are? We're going to try and get those as close as possible and as untangled as possible for this. 5, 6, 7. So these are all the sensors right here. These are the outputs for them. And we're just gonna shrink the PCB. I'm wondering if I can just put that there, and shrink it a bit more. And again, the smaller it is, the cheaper it is, but also not just trying to be cheap, but also when this is made, like where am I gonna put it? The smaller it is, the less splash damage it could potentially save itself. Just this top of this is not really that great. Actually, this and this, this one can be rotated. This one can be rotated because this is the back of the terminal. And I'm kind of debating whether or not just to put these guys close to each other. Nah, we're gonna keep it the way it was. Just because each one should get a separate, you should each get separate heat sinks, if I'm gonna do heat sinks on them at all, because that's actually the right way to do it. Instead of trying to like group them up to throw them on one heat sink altogether. And as for that, we're gonna do that. I'm gonna shove these down here. Shove them over here. I want to make this like stupidly small. All right. And you know what? I think that's gonna be okay. I am not sure at all. We are just gonna roll the dice. Because I can't tell what's right or wrong right now. We're gonna try and make it a little bit like that one, that one, that one, that one. And we're gonna raise them all up to the same level. You know what? That's fine. And we're gonna route. We're gonna use auto routing. Design rules. We are going to do. How much does that pump take? Trace with calculator. PCB trace with calculator. We're going to be using a thickness of 1 and a current of hopefully not 5. We're going to use millimeters. 2.77. No, not 5 then. 2 amps. 0.5. Okay. We're going with 1 millimeter. And run. Okay. And we're gonna adjust some stuff because I actually want to try and make it 2. What was the trace width? 2 point for 5? 2.77. Okay, so that's about 3. Okay, that works. There we go. Can I make this 3? No, I can't. Not without. Hey, nope. 2. Save it. Yep, nope. You can only go about 2. 2.7. Oh man, actually 2.77. Save. How do I send this out to DRC? Nope, no DRC here. So 2.77 actually works. Okay. Three. Nope. 2.77. Fine. Huh. Delete that. We're just gonna pop this right over. Well, I don't understand half the time why it does like these complicated routes. Three. Three. Save. Nope. Nothing wrong here. Three. Come on. No. Oh, right there, you piece of garbage. Holy. Three. There. Is this 1 to 3? Change it to a bottom layer. That's fine. There we go. I don't know why that did a top layer, but that's fine. So, in theory... Oh, nope, that one isn't good. Alright, this is the gate right here. Okay, so that's the voltage divider. Goes to the gate. The gate then that's super close. I'm doing this for 5 amps. So really kind of hoping that works. .5. I'm sorry, I'm gonna have to change this because they're just too close together. There's no way. So it can't run 5 amps, but it can run pretty close. Alright. I buffed everything else up. what did I rate it for? 4.5. Yeah, so it can do. What did I put it at? I put it at 2.5. It can do better. No. 4.75. It can do about 4.65. Yeah. 4.65 amps. So if I'm running anything bigger than that, I don't think I want to. Let me rephrase that. If I am running anything at 12 volts, 5 amps, that is 60 watts. I do not want anything bigger than that in my contraption because it'll blow the top off. The pump will blow the top off. So yeah. So wait, let me see if I can look up the one I have. Because I actually bought it through Amazon. Whee! Yes. 1.2. Alright, so it's 1.2 amps. We are going way overkill on this. 12 volts, 1.2 amps. Way overkill. So I think we'll be fine with the 4.5 amp limit. Alright. As for the rest of these are, what did I say? Yeah, 2. Yeah, these are about, for these 1mm ones, they're about 2.5 amps. That's enough to power basically 2 of the motors. So I think we're fine with that. Everything tracing wise looks all right. It's basically that. And then we're going to first save it. And then PCB. Sure, check the CRT. And we are cool. We're done. One click. Tell me how much it's worth. So, let's see if it does look up. So, for a standard board, 2 layers for 5 of them, it's gonna cost, originally it's $4, but because of their special price, it's $2. And let's see if I throw in purple, will it change? Nope. Red, nope. Blue, and I don't care. It's, yep, 1 ounce. And yeah, we're basically done. For $4 for 5 of them? Yeah. So Oh, you can even do aerospace or medical. Kelvin test. This automatically, here's the board, is quality aerospace. So you can get better quality stuff. Industrial. We're just gonna stay industrial. We want lead free. I guess we do. That's fine. It only raises it by $1.30 more. Which might be a good thing. Fully tested. Okay, so wait. Lead free. Silkscreen white. Fine. 1 ounce tinted. Board trace tolerance. I don't really need tolerance on this because we're gonna design it. We're gonna design an enclosure for it, so it can come with whatever tolerance it needs. I don't care. Confirm production file. Wait, does that add a charge? 44 cents. No, we're good. Remove order number. What is this? It distinguishes your PCB from. If you want to remove it, there'll be an extra. Oh. So there's an order number on the PCB. So that's kind of meh. 4-wire Kelvin test. This is for our resolutions. Something or other. I don't care. From being scratched. I don't care. If this was gonna be for something like high quality, I would put that, but I'm not gonna. Appearance quality, that's fine. Fit screen, I don't care if it's a little bit off. Package box with JLCP. JLC PCB logo, that's fine. Yep, that's good. Alright, so we can save this to cart. Why can't I save this to cart? Is it the... Can't... Oh, I have to choose the country first. And with that, we're gonna consider this done. So now I need to order this. I have all the parts here, in my house. So we should be able to rock and roll once this arrives in like 2 to 4 days or something. But then again, I have to go to a funeral, Monday through Wednesday, and Sunday through Wednesday. Get back Wednesday, leave Sunday, and well, hopefully it'll be done by then and sent to me. But with that, hopefully this will be done and we can get this up and running soon, because I do need to plant them. I do need to plant my plants. I'm reconsidering a bunch of things, but it's mostly gonna be lettuce and maybe some bok choy, because those two seem to be, bok choy seems to grow really fast, and lettuce also seems to grow really fast. I just harvested some bok choy from my planter today because they were dying. I think there were too many grouped up in one pot, so I took a few out, and hopefully now the ones that are there will survive and grow bigger and bigger, and hopefully it'll be full length bok choy. But for this one, hopefully we'll have salad for the rest of the summer once it starts growing. So, with that, thank you guys for tuning in and watching. I'll catch you guys next time. When we finish this up, solder everything together, and install it on the planter. And then test it out. Because we actually haven't tested the pump out yet, which is actually pretty scary. Now that I've designed the board for it, we don't even know if it works. But hopefully, fingers crossed, it does. And if not, we can always get a 12-volt motor that can do it. Hopefully does. But if it can't, it can't. If it does, it does. That's great. So, anyways, see you guys next time. Bye. Tomorrow we'll play some video games. Bye, y'all.